This is a 10 MHz low noise oscillator from the Wenzel. In this video I will look at the sideband noise, the composite sideband noise at close range. To that end I have this set up, you can see here. It is two direct conversion receivers, two local oscillators and various hybrids and Schottky diode mixers. And here's an audio amplifier, and finally a A to D converter, a 4-channel ADC, the UADC, this one from Link RF. And feed supply voltages are well decoupled by these big capacitors. And here is a block diagram of the setup. Here is one of the direct conversion receivers, and here is the other. Within the red box there is a PLL system, because one of them has a frequency control input. It cannot control a wide frequency range, quite small. And there is a time constant in the PLL amplifier that is adjustable. Each receiver starts with the oscillator. Then there is a 20 dB coupler to pick up a signal to send into the PLL system. And then the signal goes to a hybrid that splits the signal into two equally strong signals. And then there are two mixers, one here and one there, and they are fed from a 90-degree hybrid to generate I and Q when mixing with the same phase here, or maybe the opposite phases. Here is a low-pass filter, and then here is the arrangement to feed a signal into the two receivers. The device under test, attenuator, couple something into the line here and also take out what goes through here. That's the signal from the device under test, as well as the signal sent from the signal generator. And the signal is sent into a splitter, a hybrid splitter, and then one signal goes to this part, which is channel 2 receiver, and this goes to the other part. And there is a low-pass filter between the signal source and the hybrid and mixers, because the mixers reflect things backwards that create problems when it reaches eventually the oscillators. It is very important that the oscillators are well isolated from each other, because if some signal is sent from one oscillator into the other here, then there will be some frequency pulling, and that results in a correlation between the signal from here and the signal from here. That is a correlation in the noise sidebands close to the carrier. So it was necessary to insert the 20 dB attenuator to reduce the coupling. I mean, the signal otherwise would go this way, here, reflected on the mixer, or the coupling through the mixer, and then back here and into the other oscillator. So attenuators and buffer amplifiers before the mixer. And this PLL amplifier is just an op-amp with a resistor on the output that can be selected for different time constants. And here in the frequency control input, there is a big capacitor, 30 microfarads, tantalum. The signal is going this way, as I just said, and the hybrid here does not just have a 50 ohm resistor, it has an impedance match here, because some of the local oscillator that comes in here is reflected on the mixers, or even though they are terminated properly, there is some reflection, so the oscillator goes here, reflects, goes back here, through the hybrid, and through the low-pass filter at 10 megahertz. The overtones are not coming through, but the fundamental is. And then it goes here. And if the impedance seen here is not the same as the impedance seen here, there will be a reflected signal going this way, and then again through the mixers and through this hybrid and back to the other local oscillator. So it's important to have this coupling very low, as well as having this coupling very low. It would be better to insert isolation amplifiers after this hybrid, because they wouldn't degrade the system, because the noise they add would be not correlated between the channels. But I have a limited supply of amplifiers suitable for this task. And then the signal source I can inject here comes from an HP 8657B that has a finer stepping than the A version that I usually use. This coupler goes through a 30 dB attenuator. That is to reduce the signal that is sent back from the spectrum analyzer. It sends noise, and I don't want that to go into the measurement system. And after the 30 dB attenuator, there is a hybrid to split the signal into two equal signals, one for the spectrum analyzer and one for a Perseus receiver, which can look at much higher resolution and better sensitivity compared to the spectrum analyzer. I'm using Linrad under Linux, and here you can see the setup. 4 channels and 4 input bytes for each sample, 32-bit. And the sampling rate is 11.025 Hertz, 11 kilohertz. I'm using a low sampling rate because I want very narrow bandwidth, because I'm studying the close range noise in this video. So I'm running in SSB mode, that's D, and I press X to show the parameters, P. So I have set the FFT size, the maximum. I set the bandwidth 1 Hertz and I get 0.84 Hertz. And a Gaussian window and a long storage time, because I want to have many averages on the main spectrum. And correlation is enabled. The bandwidth reduction is 8 times, 2 to the power of 2, and also here a Gaussian window and a long baseband storage time, and that's it. So I start processing, and I have to wait for a long time because it takes a lot of time to fill the 65,000 samples. Well, here we have the spectrum. and I click at the center of the signal. And you can see we have the marker here that it is running, but nothing happens as yet. I have to wait. And waiting and waiting. Here you can have the first line of the waterfall. And here we have the first spectrum. And I clicked at the center, so it comes at the center. And you have the first waterfall line here. So I switch off the camera and wait for a while. Now it has been running for about 40 minutes. I can read the level here, and it shows 0 because I calibrated it to show 0. Almost 2000 correlation spectra are averaged in the green track, while 400, which I fed in here, are averaged in the yellow trace. And as you can see, the difference is small. So 400 is about as much as I can use in this situation. I will check the noise floor at a separation of 5 Hertz. It's 2, 4, 5. So I click here and wait for a little while. Now I have collected 3800 correlation spectra, the green, and you can see it looks very nice here. The yellow looks peculiar. That's because this peak you see here is an artifact in one of the oscillators. These kinds of bursts of false resonances from the crystals, and it's present only in one of the 2 oscillators. So I have to avoid this frequency. Anyway, I can see 4.4 dB of difference between the white track and the green track. So I write that down here, 4.4, and it was 3900 averages, and I read out the levels here. Channel 1 minus 110.2 and channel 2 minus 113.7. Now I am at 10 Hertz separation, as you can see here, or maybe here, and I have a new level for the noise floor, minus 119.8 and minus 123.8. The correlation is now up at 5075, 5100 roughly, and I see 7.9 dB as the difference between the green and the white track. So here is what I have seen so far, and it is with a time constant of 1 second here for the PLL. I will increase that to 10 seconds. So it is 2 steps on this switch here. 1, 2. And then I have to clear the correlation, that's Alt-Z, like that. Now 4,200 averages. So the green curve is now lower than it was before. It is 13.9 dB below the average power. The two channels are at minus 120 and minus 126. And they compare with the previous at the time constant of 1 second. Now it is 10 seconds. And the performance of the channel 2 local oscillator has improved by about 2 dB. And I attribute that to changes on the crystals. The crystals are running very hard in these oscillators. So I will look now at an offset of 5 Hz. Now with 5,100 averages I see 6.3 dB as the improvement of the correlation spectrum as compared to the normal power spectrum, and that is at a separation of 5 Hz and a bandwidth of 1 Hz. And the channel levels are minus 110.3 and minus 116.1. So the increased time constant from 1 second to 10 seconds has changed the influence of the correlation from 8 to 14 dB approximately at 10 Hz, but from 4.4 to 6.4, that's only 2 dB at 5 Hz. I will now increase the time constant one more time, and I go up to now a factor of 10, that is 100 seconds as the time constant for locking, and I have to restart here, so I press Alt-Z to clear the correlation spectra, and then I wait. Now 12,000 averages, and the correlation advantage is 17.8 dB. Now that seems very much, but there is a significant difference between the two channels, so it is actually more like 15 dB. Oops. Well, at the moment there is this bug in Linrod that prevents me from doing a readout of the levels. Well, I can read it manually. It is minus 109 on the channel 1, minus 109. This is not as accurate, but it will be good enough. And here is minus 117. Minus 117, and the advantage was 18.2. It varies a little bit because this average varies a little bit. 18.2. and it's 100 seconds at 5 Hertz and 12,000. Note that we now see a difference between channel 1 and channel 2 at close range. Previously it was not visible because the phase locking was fast enough to make the very close range noise, phase noise, the same for both oscillators. But now with the 100-second time constant, they are no longer locked at such a range as 1 Hertz anymore. Now some more time has elapsed. It's 13,500 and the correlation advantage is 17.2 now. And I was able to do a readout now. So I'll write down these numbers. I have shifted the frequency to an offset of 10 Hertz and I've not cleared the correlation, so it is now 15,000 and the advantage here is 17 dB and the channel power levels are minus 119.1 and minus 126.2. I have changed the frequency offset to 20 Hertz and I have not reset the collection, so it's now 16,500 and the advantage at this offset is 16.1. And here are the levels of the two channels. The frequency separation is now 40 Hertz from 232 up to 272. And I have not cleared the correlation average, so it's up at 17,600 now. And the correlation advantage is 13.7. And I read out the channel levels, and 138.5 and 143.0 for the two channels. I am now increasing the time constant again for the PLL, and it is now 300 seconds. And then I have to clear the correlation averages like this. I press alternate Z and it starts to collect correlation averages again. Now I have collected 12,400 averages and the correlation is 14 dB. And I look for the channel levels, and I hit this bug again in Linrad, but I could get it out for half the spectrum and that will be accurate enough. 138.8 and 143.2. As expected, at the separation of 40 Hertz, it doesn't matter whether the time constant is 100 or 300 seconds. I have now collected 13,200 averages. The advantage is 14.8 dB. And I read out the channel levels, 129.4 and 35.2. Now I'm collecting at an offset of 10 Hz with a PLL time constant of 300 seconds. I have 15,200 averages of the correlation spectra, and the advantage is 16.2 dB. And I evaluate the channel levels 119.5 and 127.6. Now I'm running at 5 Hz offset. The difference between the two oscillators is clearly visible here. The green track is channel 1 and the red is channel 2. Channel 2 is the one which is locked to channel 1 with the PLL. I have collected 17,000 averages, and the correlation advantage is 19 dB. And the channel levels are minus 109.7 and minus 118.8 dBc per Hertz. The correlation spectrum doesn't look right. These minima here and here, that is not what I expect. Maybe this is because of inadequate precision of the Fourier transform. The size is 65,556 and the dynamic range is very high. And the requirements of that is going to be eased if I make the transform smaller. So I have changed the first FFT bandwidth to 2 and find 32,768 for the size and with a bandwidth of 1.61 Hz. After changing the first FFT size, I have to redo the calibration. The error is 0.6 dB. So I add 0.6 to the calibration and then I read 0 again and clear the graph. And I move to an offset of 5 Hz. 2, 4, 5. That's here. And the computation of the correlation advantage uses the same bandwidth as I have selected here. That's 1 Hz. Now, that means that I'm selecting just one bin. But here you can see the shape of the signal, and I can no longer go closer than about 5 Hz. We will see after a while where this ends. Now it's been running overnight, 33,500 averages, and the correlation advantage is 16.2 dB. And now the green trace looks more or less perfect. Means it doesn't have those phenomena that I wanted to avoid by making the transform smaller. So it means I have to introduce dual precision floating point arithmetics for the first FFT to allow a selection of that. And I go back now, it is 16.1. It goes up and down because the white trace has some noise in it. It's the average of 800 spectra. I evaluate these levels here, and they should be the same as they have been before, or at least close to that. And here is the baseband graph, and you can see the difference between the oscillators. It seems to increase. There shouldn't be any difference in the baseband graph due to the change of the first FFT size. $37,200 averages 15.7 dB correlation advantage. That's at 10 Hertz separation, and channel levels are like this. Frequency offset is 20 Hertz now. I have collected 41,600 averages. The advantage is 15.6 dB. And I evaluate the channel levels. So and here are the channel levels. I had to reset the correlation averaging because of a problem with the computer. But now I have collected again 24,500 or 24,600, and the correlation advantage is 13.8 dB, and the separation is 40 Hertz. $230 up to 270. And I look at the channel levels, 138.5 and 143.2 dBc per Hertz. I have now disconnected the test object. There is some leakage here. We can see in the correlation spectrum and also in the normal average power. This is a spur. I don't know where it comes from. I have collected 29,500 averages. The correlation advantage is something like 21 or 22 dB, but it's not very flat at all. I don't know the reason for that. Anyway, the noise floor here is minus 152 or minus 153 dBc per Hertz. And to that comes a 20 dB advantage from correlation. So the limit for this measurement should be somewhere around minus 170. I have changed the requested bandwidth to 5 Hertz, and that gives me 6.7 as the bin bandwidth of the first FFT transform, with a size of 8192. I have set the bandwidth to 10 Hz, and I'm collecting now the carrier. And I have recalibrated in order to make it show 0 here, as you can see. I will look at the separation of 100 Hz, 6.24, 7.24, that's here, and clear the correlation spectrum. It runs much faster now with a smaller transform. And if you were observant, you should have noticed that the offset is now 1 kHz, not 100 Hz. Now, with 49,000 averages, the correlation advantage is 14 decibels, and channel 1 and channel 2 are similar at 143.7 and 144.5. That is dB below the carrier in a bandwidth of 10 Hz. This is 2 kHz, 55,000 averages, 14.2 dB advantage. And the channel levels are 144.23 and 145.0. Here is 4 kHz offset, 65,000 averages, 14.1 dB. And channel levels minus 144.6 and minus 145.4. Offset is now 500 Hz, 100,000 averages and 12.8 dB correlation advantage. And I try to read the channel levels, but here we have minus 143.3 and minus 144.2. Now the offset is 200 Hz, and the correlation advantage is 12.4 dB at 107,000 averages, and channel levels are minus 141.2 and minus 143.2, and that's in 10 Hz bandwidth. This is a separation of 100 Hz. The correlation advantage is 11.1 at 113,600. And the level of the channels is minus 138.0 and minus 140.9. This is a separation of 35 Hz. The advantage is 14.5, and the channel levels are 127.0 and 131.6. I am evaluating at 35 Hz rather than 40. That's because of this 50 Hz spur you can see here. It looks weak, but it destroys performance for the correlation. If I move the frequency a little bit, like this, so it takes a little time. Now that 50 Hz spur is close to the filter center, or it's even within the filter passband, then the correlation advantage becomes much smaller. Because in the correlated spectrum, this is a strong thing. And I have to move, and I can look at the correlation advantage here while stepping downwards in small steps. Here it's okay, but here it's no longer okay. And then I can look at where that spur comes. And you see, this far away, it is still within the range used to compute the difference between the correlation spectrum and the average normal power spectrum. I have now inserted a 10 dB attenuator right on the device under test, the Wenzel oscillator. And I have to recalibrate to make it show 0 again. Like this. Now it shows 0. And I will repeat measurements now with the 10 dB weaker signals. Ideally, the result should be the same. The separation is now 1 kHz, and I have 14,000 averages and a correlation advantage of 19.2 dB. And channel levels are now very similar because the system is no longer dominated by sideband noise from my local oscillators. I am collecting averages of the correlation spectrum at a separation of 1 kHz. Now 200,000, a little bit more, and 24 dB in correlation advantage. But the correlation spectrum is still a bit noisy, as you can see, so I will have to wait another day or so. Now I've collected 383,000 averages, and the advantage doesn't increase anymore. It goes up and down a little because of the noise in the white track, the average power spectrum. The noise band, the green, seems to be a little bit narrower, but not much. I don't think it is meaningful to wait anymore. So I read out the from here to here. So here are the channel levels, 134.1 and 135.0. At 100 Hz, the correlation advantage is 17.5 dB, 460,000 averages now. And the levels are 132 minus and minus 133.6. So I have written down all the numbers that I have collected now. And here I will put them into Excel and compute the final result for the sideband noise. So first column is frequency separation, PLL bandwidth, S-meter levels in channel 1 and in channel 2, bandwidth in hertz, and the number of averages. And what I read in the correlation, that is the difference between the white and the green track on the screen. The maximum possible correlation, it's round, I don't want so many decimals, the logarithm of the square root of F3, that's the square root of the number of averages, and convert to decibels. And then power, that is the white track on the screen. It is the sum of the powers in the two channels, which I have here. I have them in decibels, so I have to go over to the linear power scale and then go back to decibels after having taken the sum. Now the white track, it's calibrated in such a way that the green curve is 0 at the same point where the two channels both are 0. So summing the two gives a 3 decibel too high value. So I have to subtract 3 decibels. And finally round it to 1 decimal. And then I have something I call the correlation margin here. And that is the average power from the two channels in decibels. It means it is the product of this and that. And then normalized means divide by 2. Because the correlation is a phase dependent multiplication of the two channels. And then minus I3, it's the power we have, and H3, it is the maximum correlation we could have, and G3 is the correlation we read. And then correct for the bandwidth, which is E. So correlation margin, when it is very small, the result is not reliable. And here is the size of the Fourier transform. Having 65,000 is probably not quite accurate. And then having on higher separations 8,000 samples is even better. But I cannot go so very close then. Now, looking at the numbers, I will print this to a paper before doing that. I looked at two separations, 1 kilohertz and 100 hertz, when having the signal attenuated by 10 dB. These two compare extremely well with the result when I didn't have any attenuator. 100 hertz, it's here, 160.3, and here I got 160.2, 1 kilohertz, 168.5, and 1 kilohertz here, it's the one here, 168.1. So that's 0.4 dB difference. So that's within expected errors. When looking at the results for having a large transform, and and that is probably most inaccurate at large separations, which means 40 Hertz. And I go for the 300 seconds time constant, so it is this value to compare with 40 Hertz, which is here. So they agree within 0.2 dB. 20 Hertz, 147.1 here, and 20 Hertz here, 146.2. That's a 1 dB error. Uh, 10 Hertz, 138.1 and 137.3. That's 0.8 dB. So the errors are small. And then you have seen already in the video that at very close range, means 5 Hertz, time constant 1 Hertz here, and time constant 10 Hertz here, that differs by almost 3 decibels. And 100 Hertz, that differs even much more, but I didn't wait long enough. And time constant 300 Hertz, it is this one, goes to 131. So from 116 up to 131 for having different time constants for the PLL. It's really important to have a slow enough phase locking, because otherwise the two oscillators will have correlated phase modulation because of the PLL. I will plot the values that are in green. It's the set with 8000 FFT from 1 kHz to 35 Hz, and it's the set with 32,768 transforms, and both of them with 300 seconds for the time constant. And here is what it looks like. A regular curve, and it's not meaningful to look closer to this now. It will be later when I insert things between the oscillator and the test system. It's interesting, however, to compare with channel 1 and channel 2, which is the noise of my two low noise oscillators. So they are significantly less good than the Wenzel oscillator at close range, about 10 dB from here to here, and nearly 20 dB from here to here. My low noise oscillator, I measured them before, looks like this. They go down to this level, minus 190. They go below that at wide separations. At 1 kHz, 172, and that's the sum of the noise from both oscillators, because that was the only thing I could look at previously. Now the channel 2 point at 5 Hz, well, at 10 Hz I observed minus 128.2. 10 Hz, that's here, 128.2, that's here. So it means I have an oscillator that is at this point, and then it goes down, and it goes below 195 at 100 kilohertz. So, well, I find it a little bit interesting. This is a plot from a FSWP, a Rode and Schwarz signal analyzer. It is the measurement of the very same Wenzel oscillator that I'm studying now. And the results look very close, but there are some odd things. What I'm looking at is the sum of the AM noise and the phase noise, and the FSWP can measure both. So the blow track is the phase noise and the black trace is the AM noise. And it looks like what I have is a pure phase noise, and that there is something wrong with the AM noise measurement of the FSWP. Particularly at frequencies around 20 Hertz and about 100 Hertz. I attribute that to a not properly filtered supply voltage in the measurement with the FSWP, but I don't know. And then, when coming to large separations, the largest I could do was 4 kilohertz. It looks like my measurement is about 3 decibels above the phase noise. And since I'm measuring both the AM and the phase noise, and it's expected that in the flat region out here, AM noise and phase noise should be equal. I find this a good agreement between the FSWP and what I have been finding so far. And once again, here are the numerical values.